Hey Precalc, these are your Trig Day 12 notes. Today we are looking at what are called the sum and difference identities. So we're going to be starting over the next few days here, building many more identities onto our list of ones we already know. And if you're like, wait, we know identities? The answer is, of course we do. We know the Pythagorean identities like sine squared plus cosine squared is 1 and 1 tan is a secret. We know quotient identities like tan is sine over cos. We know reciprocal identities like, I don't know, cosecant is 1 over sine, right? So we have a lot of identities that we actually already know. Here are 3 more that we're going to add onto our list. And with that being said, we'll then see where these identities come into play when we're starting to evaluate and do more with trig evaluating. So the very first one says, what is sine of a plus or minus b? So a and b represent 2 different angles, and sine of the sum of 2 angles is not equal to sine A plus sine B or sine A minus sine B. Sine is not a distributive process, okay? So it's not an operation, it's a function. So what turns out to be the case is if you do sine of the sum or difference of 2 angles, it would be sine A cosine B. And then that plus or minus is going to go in the middle, cosine A sine B. Much more complicated than it initially looks by just saying, oh, it's sine A plus sine B. It's just not the case. And there are some proofs that we can look at if you're very curious about why this is the case. But sine of the sum of 2 angles would be sine, cosine, cosine, sine. And if it was the difference, it would be the same thing with a minus in between. So these look like they're going to be complicated to know, but we actually have some fun little chants that we'll use to remember them. So sit tight for a second. So what about cosine of the sum or difference of 2 angles? Well, for cosine, it's going to be cos A, cos B. And then over here, you're going to have sine A, sine B. So cosine looks easy, except you have to be a little bit careful about the middle, because if it's cosine of the sum of 2 angles, in the middle, it's a difference. And if it's cosine of the difference of 2 angles, in the middle, it should be a sum. So for cosine, we have to change the sign in the middle. I'll give you a way to remember that too. All right, tangent, here we go. Tan is going to be a fraction. It's going to be tan A plus or minus tan B. That's the top of the fraction. The bottom is 1, and then whatever the sign is on the top, you switch it for the bottom. So the bottom has a minus over plus, and it's going to be tan A times tan B. If you're like, oh man, these are looking a little scary, don't worry. We're going to practice with them, and you'll use them so much that you'll think, how did I ever not know the sum and difference identities? Are you ready to chant them? If you're at home, I will have you repeat after me. Ready? Sine of A plus B is sine, cosine, cosine, sine. And at home, you're saying sine, cosine, cosine, sine. All right, for cosine, what's the chant? Cosine, cosine, sine, sine, cosine, cosine, sine, sine. All right, and then finally, tangent. What's the chant for tan? Tan, tan, 1 tan, tan. Tan, tan, 1 tan, tan. Okay, so you guys have these, I promise. We're just going to chant them each and every single time we go to use one of the sum or difference identities. A couple other things to pay attention to. For sine, the sign in the middle stays the same. Sine, sign stays the same. Cosine, C-O-S, change of sign. There's a change of sign in the middle, so that's a good way to remember this, that there's a change of sign. For cosine in the middle, if it's a sum, we're doing the difference. If it's a difference, we're adding. Those are good little tricks that have helped students over the years to remember these identities. Perfect. Moving on to where are we actually going to apply these? In example 1, we are going to find the exact value. And when I use the term exact value, to you it should mean like don't touch your calculator. Of sine of 105 degrees. Okay. To find the exact value for sine of 105, first and foremost, if you sketch 105 degrees, what I want you to think about is that 105 is in quadrant 2, and that we have a reference angle here of 75 degrees if this is 105. We don't have a triangle with special sides if the reference is 75. What are some special triangles that we do have references for? So what we know is that if the reference is, let's say, 30, 45, or 60, we have special triangles that have those as reference angles. In quadrant 2, what would be the same angle with these reference angles? So 30 degrees in quadrant 2 would actually be 150. And 60-degree reference would be 120. A 45 reference would be 135. So these are also maybe familiar angles to you because they have references of 30, 45, and 60. In quadrant 3, references of 30, 45, and 60 would be angles like 210, 225, and 240. This is a reference of 30, 45, and 60. And in quadrant 4, some special angles that we might be familiar with would be things like 300, 315, and 330. This is a reference of 60, 45, and 30. So these are good angles to pay attention to because here's what we're going to do. If these all have special ratios using 30, 45, and 60 as the triangles, we want to figure out how can I get 105 degrees as either the sum or the difference of two angles that are special. And as soon as we do that, I like to work with quadrant 1 first, see if I can get it pretty easily. As soon as we write down these and we're like, okay, these are the special ones I need, 105 is pretty easy to come by. If you do sine of 60 plus 45. Okay. So if we say that 105 is 60 plus 45, which is true, we can use the sum identity for sine to be able to figure out what this is. By the way, this does not equal. I'm going to write what it doesn't equal because I said it from the beginning. You can't distribute this sign. This is not what it equals. That's no good. And sorry, don't like that. All right, sine of 60 plus 45. How am I going to do this? If this is the A and this is the angle B, we need to do sine, cosine, cosine, sine, sine, cosine, cosine, sine. I know you're chanting it at home, so I'm just going to follow along with you. All right, here we go. It's going to be sine 60 cosine of 45 degrees plus cosine 60 sine 45 degrees. Just follow the pattern given that this is angle A and this is angle B. Sine, cosine, cosine, sine. All right, I'm only going to do this maybe once, maybe twice if you're lucky today. I'm going to draw two triangles and remind you what the pattern is for the sides in a 30-60, 90 and a 45-45, 90. If 60 is the reference angle, across from that's radical 3, so this would be 1 and 2. If 45 is the reference, we get 1, 1, radical 2, like that. Okay, so if those are the triangles, let's start filling in what we know. Sine of 60, let's see, opposite over hypotenuse is radical 3 over 2 times cosine 45. Cos 45 is adjacent over hypotenuse. That's 1 over radical 2, which I'm going to rationalize in my head to radical 2 over 2. We've done that enough that that shouldn't be a big jump for you. 1 over radical 2 becomes this as a ratio. Plus cosine 60. Adjacent over hypotenuse is 1/2. Sine 45 is also going to be radical 2 over 2. Because 1 over radical 2 rationalizes to this. All right, we need to keep simplifying here. Radical 3 times radical 2 is radical 6. You can multiply those numbers underneath over 4 plus 1 times radical 2 is radical 2 over 4. And the great thing about this is oftentimes you already have a common denominator, which means you can add those numerators. Radical 6 plus radical 2 is radical 8. Wait, no, it's not. Mr. All, don't do that. That's what you'd be saying at home. Okay. All right, radical 6 plus radical 2 is the simplest you can get the numerator, but you can write that as all over 4. Okay. Now, if you're wondering, wait, is there a way to check this on the calculator? This is the exact answer, okay? There's no decimals at all. Well, the answer to that is yes. You can check this. Now, make sure you're in degree mode to check because we want to type in sine of 105 degrees. Sine 105 is this, 0.9659, blah, blah, blah. Fancy fraction, oops, hold on. Fancy fraction, radical 6 plus radical 2 divided by 4 is 0.9659, blah, blah, blah. It's the same exact thing. So you can confirm on the calculator that your decimals match, but to be honest, I really don't anticipate you doing that too much. We're going to see this type of answer come up over and over and over again. Okay, so that was all example 1. Let's go a little bit faster for example 2. In example 2, we're going to evaluate cosine of pi over 12. And if you look at pi over 12, you might be thinking, that doesn't sound like a special one. We're used to like pi over 6 and pi over 3 and pi over 4. Yeah, pi over 12 is not necessarily one of the special angles, but we can add or subtract some special angles to be left with pi over 12. I think that even though I'm a big fan of radians, these types of questions where we have to find the exact value, by the way, those are the same directions, find the exact value. I think it's much easier to think of it in terms of degrees. So what is this in terms of degrees? Well, if pi is 180 degrees, 180 divided by 12 is 15 degrees. Okay, now that I know what we're working with in degrees, I want to think about which of my special angles up here can I add or subtract to get 15? And I usually start with the quadrant 1 options, and if that's not enough, I can move over to quadrants 2, 3, or 4. But I can do this in quadrant 1, can I? I want to figure out two angles that either add or subtract to give me 15. You actually have two pretty good options. I'm going to do this as 45 minus 30. But if you do 60 minus 45, that's also 15, and you should get the same exact answer. Okay, so 45 minus 30 is the initial start. For cosine, what's the chant for cosine? Cosine is cosine, cosine, sine, sine, cosine, cosine, sine, sine. Okay, here we go. It's going to be cos 45, cos 30. And then in the middle, get ready, plus, because for cosine you have a change of sine, change this to plus, sine 45, sine 30. Okay. Now I'm going to use the same exact triangles really as up here to fill in what these values are. Cos 45, radical 2 over 2. I'm going to cheat and say, you know what? We did these two just a moment ago. We just did cos and sine of 45. What about cosine of 30? Remember, 30 is actually up here. You don't have to draw a whole new triangle. Cosine of 30 would be adjacent over hypotenuse. That's radical 3 over 2. Sine 30, very similarly, opposite over hypotenuse is 1/2. So if I add these up, we get radical 6 over 4 plus radical 2 over 4 equals, well, wait, isn't that the same thing I just got up here? Radical 6 plus radical 2 over 4. And like I said, you're going to see that answer come up a lot. Here it is again. It may be equivalent forms to this too. Like you might see like a minus sign in there sometimes, but are you telling me that cosine of 15 is the same exact decimals, all these others? Yeah, sure is. Okay, sine and cosine have this special relationship. They're called cofunctions of one another. Sine and cosine of complementary angles have the same value. So sine of 75 and cosine of 15 are the same. These angles are complementary. They add up to 90. So just as a quick note there, a little bit of extra trig bonus knowledge as far as that goes. All right, let's move on and do really one more type of question today. And once we're done with this question, we'll go ahead and take a look at some more practice when we're in class tomorrow. So in example 3, I'm going to give you some information about two different angles. I'm going to say if sine x equals 5/13, and I'm going to tell you that x is from pi over 2 to pi. Then I'm going to tell you cosine of angle y is -3/5, and that y is an angle from pi to 3 pi over 2. We're going to find a bunch of information based on this, okay? So the first thing I'm going to find, I'm actually going to give myself some space up at the top. In part A, I'm going to find what is sine of x minus y. So what would be sine of the difference of these two angles in question? Oops, there's supposed to be a less than sign there. You guys can add that in. Okay, so let's talk about what we know. We know that angle x is from pi over 2 to pi, so that should be jumping out to you as being in quadrant 2. Let's draw a picture of an angle in quadrant 2. I'm going to label this angle as x. Remember that sine is opposite over hypotenuse, so that was going to be 5, and that's going to be 13. Okay, we'll stop there for now. Let's talk about angle y. If angle y is between pi and 3 pi over 2, isn't that quadrant 3? All right, so let's draw another picture over here for angle y in quadrant 3. Cosine's given, which is adjacent over hypotenuse. So that would be adjacent of -3, hypotenuse of 5. All right, and I'll give you a hint. In order to be able to complete sine of x minus y, you're going to have to find these other missing sides right here. which guess what? You know how to do that because you know Pythagorean theorem. All right, I am going to save the time because I'm not going to waste my time doing Pythagorean theorem every single time to show you these steps. These two patterns, by the way, come up a lot in sum and difference identities. 5, 12, 13 is a very popular pattern as a Pythagorean triple, it's called. You might be more familiar with this one. It's a 3, 4, 5, right triangle. If you do Pythagorean theorem with these three lengths, you're going to find that, yep, those work in an a squared plus b squared equals c squared. By the way, don't forget that those will actually be negative just based on the quadrant that we're in. We're going left, yep, that's negative. We're going down, that's negative. This information is critical to get correct because it's going to affect every other calculation that I do in this question. How do I do sine of x minus y? Well, according to the identity sine of x minus y, it's sine, cosine, cosine, sine. Sine x cosine y minus cosine x sine y. Sine, cosine, cosine, sine. Sine, the sign in the middle stays the same. Okay, now that I have these pictures drawn here, I really don't need any other information from the top. Sine of x would be opposite over hypotenuse, 5/13. Cosine of y, make sure you go to this triangle with y, adjacent over hypotenuse is negative 3/5. Minus cosine of x. Cosine of x is negative 12/13. Adjacent over hypotenuse. Sine of y, come back over here, opposite over hypotenuse, negative 4/5. Okay, now we can multiply these and multiply those. The nice thing about multiplying fractions, you just multiply the tops, multiply the bottoms. So you get negative 15 over 65 minus negative 12 times negative 4 is positive 48 over 13 times 5 is 65. The great thing is we already have a common denominator. So if you subtract the numerators, negative 15 minus 48, you get negative 63 over 65. Okay, that would be the final answer for sine of the difference of these two angles. Let's try something like cosine of x plus y. And what would that look like? All right, cosine of x plus y is going to be cosine, cosine, cos x, cos y. Change the sign to minus sine, sine. So cosine, cosine, sine, sine, but change of sign for the middle here. It's going to be plugging in a lot of those same ratios as up above, but the order in which I multiply them is different. Okay, cosine of x, just use your picture for x, is again negative 12/13. And then cosine of y, come over here, negative 3/5. Minus sine x is 5/13. And then sine y, negative 4/5. Okay, so that would be the initial substitutions there. Negative 12 times negative 3 is 36 over that same denominator, 65. Minus 5 times negative 4 is negative 20 over 65. Subtracting a negative would be plus 20 there. So 36 and 20 is 56 over 65. Okay. And last but not least, just because we haven't talked about it, let's do a tan example. Let's do tan of x minus y. Okay, here's going to be the formula for tan. Tan is tan, 1 tan, tan. I like tan. It's just a fun little chant there. So the tan on the top is tan x minus tan y. The bottom is 1 plus tan x times tan y. Okay, so it's the difference of those two on the top, 1 plus the product of those two on the bottom. Now that I have that, we're just going to use the same exact triangles up here, but we're going to only be looking at tan. So tan of x would be opposite over adjacent. So that's negative 5/12 minus tan of y. Tan y would be opposite over adjacent, negative 4 over negative 3. That's positive 4/3. And the nice thing is that those same ratios get plugged in on the bottom. So it's 1 plus negative 5/12 times 4/3. Okay. The algebra that I'm going to do here is, we have a complex fraction. So I'll show you what I'm going to do in 1 minute. I'm going to leave the top for a second. But on the bottom, I like multiplying fractions because I don't need an LCD. Negative 5 times 4 is negative 20. So I'm going to change this to minus 20 over 36. Okay. And if I look at these three denominators, the 3, the 12, and the 36, the LCD here is, in fact, 36. So I'm going to multiply the top by 36 and the bottom by 36. And that's how I'm going to simplify this without my calculator. All right, distribute the 36 on the top. 12 goes into 36 3 times. That 3 is going to get multiplied by the negative 5. Minus 4 times, well, 3 goes into 36 12 times. So there's the numerator right now. Denominator, distribute the 36. 36 times 1 is 36. Minus, oh, here the 36's cancel completely to get 20. So the top is negative 15 minus 48. 36 minus 20 on the bottom is 16. So the final answer is negative 63 over 16. And I realize TAN just has that extra level of algebra that we have to simplify the complex fraction, but use your calculator to your advantage too. There's nothing stopping you from being able to, do some operations where you subtract fractions on the calculator. I would like you to have the skills to do this using the LCD and getting rid of the complex fraction. I think if you do a little bit more practice with TAN, you'll get there and you'll feel more confident with it. But let's stop there today for the sum and difference identities. We'll do more examples just like this. We'll also do more finding the exact value questions next time we're in class. Have a great rest of your day.